Hey folks, welcome back to Advent of Code in F#, and we're at day 6. The puzzle is just unlocked, so let's take a look-see, shall we? Day 6, guard Gallivant. The historians use their fancy device again, this time to whisk you all away to the North Pole prototype suit manufacturing lab in the year 1518. It turns out that having direct access to history is very convenient for a group of historians. Yeah, makes sense. You still have to be careful of time paradoxes, and so it will be important to avoid anyone from 1518 while the historians search for the chief. Unfortunately, a single guard is patrolling this part of the lab, okay? Maybe you can work out where the guard will go ahead of time so that the historians can search safely. We start by making a map. I see a guard. The map shows the current position of the guard. Guard is facing up, so the guard has a direction. And the obstructions are shown as... Yeah, okay, we have obstructions. The guards follow a very strict patrol protocol. If they hit something, they turn 90 degrees to the right, otherwise they take a step forward. That's like a Roomba. Roomba guards. Following the above protocol, the guard moves up several times until they reach an obstacle, and then they turn 90 degrees to the right. And we move on. It's like a sliding on ice puzzle you see in a lot of video games. Okay, this makes sense. What do we need to do? By predicting the guard's route, you can determine which specific positions in the lab will be in the patrol path. Okay, we need to path it out. I need to count the total length of the path. Oh, does the guard leave the area? Yeah, the guard leaves the area. Okay, we need to count the length of the path before the guard leaves the area. Okay. We're back to grid puzzles again. Those are a staple. Those are a classic for Advent of Code. It's 130 by 130 probably. And let's grab the example. Okay, how will we go about doing this? I think we just simulated brute force. We parse the grid. And we start the path down its patrol until it leaves the grid. What's the best data structures for this kind of problem? We could just use a 2D matrix. We don't actually need the entire grid. If we can just parse out the location of the obstacles and we know the grid dimensions, that would be enough. And then for every step the guard takes, we can just figure out, is he out of bounds? Are they out of bounds, or are they hitting something or about to hit something? Yeah, let's do it like that first. So we're gonna parse out this grid into a lookup table or a list of all the obstacle locations, and then we're just gonna keep some state for the guard, like which direction are they facing and at what location are they at, and I think we're good to go. Maybe some coordinate things. I like my x-axis to be this and my y-axis to be this. Oh, that's that's like a very crooked y-axis, but I like my coordinates like this. So, or is it actually? I don't know. Often in Advent of Code I see stuff like this. If x grows, it's like the row, and if y-axis grows, it's just a matter of what you want, I guess. But we have to like be consistent about it. Okay, let's consistently do this. Growing x goes to the right, growing y goes downward. No. I'm changing my mind. X is the rows, Y's are the columns. I think this is most natural for my Advent of Code brain. Not most natural for my math brain, but for Advent of Code, sure. So when X grows, we're going to a new row. When Y grows, we're going to a new column. I'm so gonna forget this and we're gonna make a mistake and introduce a bug somewhere. Okay, so let's start parsing. We need the location of the guard and the location of all obstacles. So we need to loop over all the spots in this grid, but we also need the indices of we did this before on one of the previous puzzles, like we generated all indices and then we took a look at what's in there. Let's do something else again today. We're going to use a list comprehension. We're going to iterate over the rows. But I'm going to do list.indexed. List.indexed takes the list and returns a list of tuples containing the elements, but also the index of that element. So now let's maybe print it out to make it a bit more concrete. Yes, it's correct, but I only selected, I selected the row, the 4 as well. So it prints out the first row, it's this one, the second row, it's this one, and if we do this, the same thing for every column and every row, we have like the 2 indices. So this is like row number and the row. And we do the same for the columns. So for column number cell in a row. And yeah, let's just parse all the obstacles. So if cell equals character obstacle, then we have an obstacle. I'm just gonna introduce a quick type to make the parsing go a bit easier. Or actually no, then yield row number, column number. Row is a string. Oh yeah, we have to index here as well. Let's make it consistent. There we go. So this should print out the locations of all obstacles. 0, 4, 1, 9, 3, 2. Yeah, that looks correct. So that's the obstacles. And we need the guard location as well. I'm not gonna make it too hard on ourselves. We're gonna do the same thing. Just parse out the single element with a guard. Not the most performant, not the most ideal, but it works and I don't have to think about stuff. So yeah, win-win. And we're gonna get the single element in here. So this should give us the guard. 6, 4, 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4. Yeah. So now we have the guard location and the obstacles. Obstacles is a flat list. So looking up an obstacle is not super fast. I think if you just kept the string and did some indexing in the string, that would have been faster. That's like O1 axis. Looping over a list is a not O1, it's linear search. So yeah, it's not the fastest approach, but why not? I think a lookup table or a set will actually be faster. Let's take a look. List operations, F#. Or collections, that was the Collections. There's a great page. We've already seen it this year. There we go. Exists. It's logarithmic. Yeah, let's just shove every obstacle in the set and it'll be good enough. So let's just do set of a sequence and we have a set of obstacles, and lookups will be faster than just a flat list. Okay, so we have the guard, we have the obstacles. Now we just have to run the simulation. So for that we let the guard run until they are out of bounds. I forgot we need to bounce. And every time they are about to hit an obstacle, they turn right 90 degrees. So bounce. It's just the length number of rows. We're still gonna do off by one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10, but we have indices from 0 to 9. So this is the max row, and the max column is just take a row and do the same. And because it's a string, it's not a list, we have to use the sequence function. It's 9 by 9, that makes sense, that looks correct. It'll be bigger for input. But now we can parse and we have all the information we need to run this simulation. So let's start running. We don't know how long this simulation will be. We also don't know how... Yeah, that's the main point. We don't know how long, so we can't just map over a sequence of things. We need to have like a while true loop, a game loop. And there's lots of ways to do it. I think we can just use a recursive function that calls itself if we're not done. And if we hit like if the guard leaves the area, it's done and it can just stop working and return the full path. Or we can use something fancy called list unfold. List scan. There's a lot of sequence generating functions. But I think we're just going to keep it simple and just use a recursive function today. No need to do anything more complicated than that. Actually, list.unfold is not too complicated, but let's write a recursive function that just keeps calling itself until the guard leaves the area and see how far that gets us. Yeah. So let's do a let recursive, and the function is called patrol. We're given obstacles and a guard. We need to define what guard means, what the state is. And it returns like the final state. Yeah, so instead of a guard, let's return state. What would state look like? What do we need to keep track of? The guard has a location and a direction. So let's do a guard type first. It has a location. It's int tuples, just row column tuples, and a direction. Well, let's just introduce a new concept called direction, and that's union type, just up, right, down, left, for example. And the state has a guard, current location of the guard, or the current state for the guard. And we also need to keep track of like the path, or at least the length of the path. Will we be hitting a single location twice? We are potentially crossing distinct positions, yeah. So keeping a counter is not smart. Let's just keep track of the whole path, like every path location we encounter. So let's call that a set of visited nodes, for example. So that's a set of locations. How do you define a set? What's the type for set? Set, sorry. Oh, it's working on the... Okay, so this works. Is there another way of defining a set? No, okay. Undo, undo. There we go. So I think this is the state I'm most interested in. Current state of the guard and all the visited nodes. How do we know if we're done? Yeah, we need also max row, max column. Okay, I'm gonna get rid of obstacles. If we don't inject max row, max column as arguments, we don't need to inject this obstacles either. And we're not writing that many tests, so keeping our code like as a pure function is not super important. If we write tests, we're going to reintroduce all these things, and we'll do a proper job. But for now, let's just do a good enough job. Why am I talking about the bound, the max row, max column? Because we need, if you write a recursive function, you need to have like a when are we done to prevent an infinite recursive call. So we are done when the guard has left the area. If guard left the area, then we're done and we return state. And otherwise, the guard has to take a single step. And it's state.guard. Actually, don't really care. Yeah, so we need two more functions. And left area. So we need these two functions. Function mapping the state to a boolean to know whether we're done, and a function that takes a state and calculates the next state. And this is the one that has to be recursive, right? So let's just not let's just not extract that just yet. Otherwise we'll have to do some funky mutual recursion stuff, and that'll make it too complicated. Okay, left the area. And it's a guard, or it's a state that contains a guard, and a guard has a location, and that is a row and a column, right? So you can, in a function signature, like here, or in the signature, or in the declaration, you can also destructure. If you just care about this and don't care about the entire input, you can just break it down in the function signature. And now we have access to R and C in the function body without having to dot in. So that's an alternative to dot into things. Okay, but this is a simple bounce check. So R has to be positive. R has to be within bounds of the max rows. And same for C. So this wasn't too bad. Nothing is too bad today, actually. So that's the bounce check, and the state recursive calculation of the state is just we let the guard take a step. So what does it mean to take a step? The guard has a direction he's facing and location. We just try to take one step forward, and if there's a little obstacle at that was the wrong move, we had to turn right. And otherwise that's the next location and facing or direction for the guard. So yeah, let's just calculate the guard's next state. And that doesn't have to be recursive, so we can just define the next. So step was actually not so bad. Guard is equals guard, and we update state with guard equals next guard. So this is like the main method, our game loop, and everything else is like smaller steps. We're gonna do the obstacle check. Yeah, I like it like this. So this is becoming so simple that I'm gonna inline this thing. Can I inline? I can inline. Yeah, I can inline. Cool. But not with the shortcuts I'm used to. Okay. Refactor this inline variable. It has no shortcut. In my head, it's like Ctrl-R-I. Okay. Okay, so this main recursive loop is pretty simple. We have stop halting condition, we have recursive call. Oh, we don't have recursive call actually. So let's do the recursive call as well before we forget. So we just call into our function with an updated state. There we go. And now only thing left is to calculate the next state for the guard. So calculate the next location. Let's call it in front, and that's taking a look at the guard's direction. If it's up, we have to decrease row by 1. If it's down, we have to increase by 1. If it's right, we have to increase columns by 1. And if it's left, we have to decrease columns by 1. So that's the offset. And the location is guard dot. Let's just destructure the. Yeah, let's destructure the entire guard. So it's a location row column and it's a direction. So let's match on the direction. And let's calculate the next location by doing R plus. Let's dr dc this offset. So let's do R plus drc plus dc. So that's the location in front. And let's rename, or let's capture that as a variable as well. Is that something we can do in F# as guard? I think so. So we now destructure the entire guard so we can grab into its internals without totting. And I also give the entire guard a name so we can easily reference to that as well. This is there's no obstacle case, but we still need to take care of the obstacle case, right? Why is there a green squiggly? Okay. It's a typo. Do I care enough? Sure. So this is the next location in front of the guard. If there's an obstacle, turn right instead of going forward. If there's no obstacle, this is the new location. So if obstacles contains in front, then we have to turn right. Otherwise, we move forward, which is what we just did here. So how do we turn right? We stay at the current location, but the direction is a 90-degree turn. So let's define a new function, turn right, and we need to turn dir to the right. I'm gonna extract that into its own function. That's not what I meant. Turn right is a pattern match. This is an alternative syntax for pattern matching if you only have a single argument function, but it's just the same as saying turn right dir equals match dir with. This is just a shorthand. If we're facing up, we are turning right. So that means going right. Right means down, down, left, left, up. That's an exhaustive pattern match, so that should be good. Should be good, should be good, should be good. And I think we're done if we did not make any stakes. So let's run this on our example. That's like hammering out 70 lines of code without even testing anything or experimenting with anything. So let's patrol on the initial state. We need to define the initial state. That's one more thing we need to do, right? Where's our state? Obstacles and guard. Oh yeah. So we need guard. And direction, we are facing up. Oh, whoa, we're forgetting the main part. We need to keep track of the visited nodes. Good call, compiler. Good catch. Oh yeah, guard is a nested structure. That's more like it. So let's see how we can keep track of the visited nodes. How will we do that? Here the guard takes a step. Or we can take the current location of the guard. What's the best place to keep track of the history? Probably right here. Yeah, let's start with right here. So let's extract a variable and let's just add this next guard's location to the visited set. So we add the next guard's location to the set, and because set already dedupes, we don't have to check whether we've been here before or not. So maybe now we're done. We forgot a small detail, which was keeping track of the path. Now we do. So let's see how far this takes us. Patrol with the initial state. And goes into an infinite loop. That's not good. How do I kill execution? Oh no, I've been here before and I do not yet know how to kill execution. That's pretty bad when you hit an infinite loop. Memory is stable. Okay, so we're not really crashing, but how do you get out of this? I actually have no idea. How does one quit out of a running interactive window? Oh, close. Reset. Okay, there's a reset button. We're good. We're good. Oh my god. Where is it? What's happening? Why is my guard infinitely walking? Let's start by printing out the state every iteration. Println driven debugging. So I know it prefers string interpolation, but I don't know how to do that. So I'm gonna help, let the compiler help me, or writer. There we go. So it's exactly the same as C#, but I'm not used to these type hint things yet. Okay, so now I hope we get to see the problem, or get to figure out the problem a bit more easily. Where did my output go? can't believe this. Where's my output? I saw it like when it was running, and then I press kill. Yeah, this is exactly what I would want to keep. Oh, pressing X really breaks it. Can I not halt execution? No, okay. That's a shame, actually. Let me just grab everything, kill out of it, and take something that does not keep. Printing new stuff. Out of bounds is definitely not working. Yeah, let's say that out of bounds is not working. He's like off in the far distance. He's gone underground, I think. Okay, so that's the problem. Why is that a problem? Why is left area not working? Ah, I did not write a left area. I wrote a he's within bounds. So I did like the reverse. So I'm just gonna not think about it and reverse my my function. I just negated it. So this will probably be better. We don't need the printfn if this was the only problem. F#8, is that actually the latest version of F#? We're at 6.4 and we have an empty set of visit nodes. That can be right either. I'm having troubles with this inbounds thing. That's interesting. Our guard has not moved. 6.4. 6.4. Let's take a look at what's happening here. 9. 9. Oh, this does not look correct. Ah, this happens when you just hammer out 70 lines of code, right? It did not improve. Let's play around with this inbounds thing. And I'm not gonna do this. If we're writing tests, we're gonna make it more context independent. I promised before, so let's do that now. Let's get rid of this whole thing. And let's see where we call it. Which was inbounds, right? Yeah, we can keep this. We can just dot into the location. There we go. So everything compiles now. Let's play around with this inbounds thing. Six, 4, right? Okay, parentheses required. That's doing what I expected to. That's actually doing what I wanted to. This should also be good. Yeah, and then we hit. Yeah, okay. So it's the problem does not appear to be in bounds, or at least not in the row part. And I am convincing myself that it's not in the column part, but let's stop convincing and let's start verifying. That's in bounds. That should not be. Yeah, this is inbounds. And this should not be. Yeah, all works out just fine. Then the thing that could be wrong is here. How can that be wrong? What am I missing? This is like every bug ever. It's not like this is a special case. I ask myself that question like every hour or so when I'm programming. How can something this simple be going wrong? So yeah, let's dive into what's going on. It's actually doing stuff, right? Why is it working now? What did I change? I don't understand. It does a lot more correct stuff now. So maybe I did not send all my code to the REPL. I was hunting a ghost bug. Or maybe I changed something unintentionally. I don't know actually what I did, but okay. This looks better. So let's get rid of this. That helped us find the column bug. Let's see if this is the correct answer at least. We need to count the distinct positions. So let's grab the final state and let's count the visited node set. $42. Is that because the starting position is not supposed to be in there? So it's 3 to the right of that obstacle. 3 to the right of that obstacle. That appears to be in there. How can I have an extra... Oh, because he's out of bounds. Yeah. In the last iteration, we are not in bounds, but the location has already been shoved in here. That's too bad, actually, right? That's too bad, actually. I can just subtract 1, and that would be enough for part 2. But then our visited set has like 1 too many elements. And that's not really super functionally correct. Like if I were to do this in actual production code, I would not be happy. I would be like putting a bomb, a time bomb somewhere that would go off when you least expect it. What if we add, instead of adding the next guard's location, add the current location? Something like this. So every time we are going to take a next step, you just keep track of, okay, we were here. Does that sound better? It does sound better. I don't know if it's actually correct what I just did, but good enough. Okay, so this is simple enough to just inline. There we go. And let's do something about the indentation. I don't know if I prefer this indentation now that I see it, but okay. Can I do more? I can do more. Okay. So this is appears to be correct enough to get the right answer for the example. Let's see if we can get the right example output for our actual input. So let grid equals example. I'm just gonna rework my script a bit so I have one place where I reference example. I think I got all locations. Yeah. So this works for the example. Yeah, and let's run it on input. We're still printing out tons of stuff. Let's stop printing out tons of stuff, because that will take us a while. And it appears the simulation has ended. What's our end result here? 5,300 and something steps. Okay, cool. And that's even correct. Good job, us. We had a couple of bugs in there. And I think it's due to my stubbornness to refuse to test. but that's like a common thing for me during these puzzles. Okay, we solved part 1. Let's take a quick look at whether or not we can hammer out part 2. While historians begin working around the guard's patrol route, you borrow their fancy device and step outside the lab. From the safety of a supply closet, this is so Metal Gear, you time travel through the last few months and record the nightly status of the lab's guard post on the walls of the closet. Returning after what seems like only a few seconds to the historians, they explain that the guard's patrol area is simply too large for them to safely search the lab without getting caught. They are pretty sure that adding a single new obstruction will not cause a time paradox. They'd like to place the new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab safe to search. That's smart. To have the lowest chance of creating a time paradox, the historians would like to know all of the possible positions for such an obstruction. The new obstruction cannot be placed at the guard's starting position. The guard is there right now and would notice. Yeah, makes sense. So in the above example, there are only 6 different positions where a new obstruction would cause the guard to get stuck in a loop. Okay, so I was thinking maybe we can brute force this, but probably if we just take like all the... How do you create a loop? Interesting. So yeah, okay, we can put 1 extra obstacle in there. And you can do that in many different places, and it would create many different exotic shapes. This is like a donut loop. This is like a very involved roller coaster loop. Okay. Okay, that's a lot of looping. It doesn't really matter what you choose to use as an obstacle, so long as you and the historians can put it into position. Having enough options that you can find one that minimizes time paradoxes. And in this example, there are 6 different positions you could choose. When do we know? Okay, we need to calculate all locations that cause loops if you put a single obstacle in there. How do we detect loops? Because these loops cross over each other. I think if we not only take a look at the location, but also the guard's direction. If like we hit a location and the guard is facing a direction it was facing before at that location, it's loop time. It's loop time. So that's loop detection down. I think we can figure that out. We could brute force it, like going over every location, trying to put a new obstacle in there and check whether or not we introduce a loop. Sounds expensive though. But I don't know if there's much optimization. We could if we kind of know. Oh, that's maybe what part 1 was for. We know the original path. See here, would that make sense? We know the original path, so we can introduce an obstacle on the original path, which is everything the guard would visit. And we only have to place 1 obstacle. Yeah, this will work. If we could place multiple obstacles, this approach would not work at all. But because we can only place 1 and just 1, this will work. We know the current path, and we just try to dump an obstacle anywhere in the guard's path. That's way more efficient. So let's try that. Instead of ripping out everything, we'll build on what we have right now. So we just continue on. We have the visited set. And that path is like all the nodes. Let's grab the example first so we can see a smaller example at work. And this is a somewhat involved exercise over a puzzle already. Jesus. It's what, day 6? It's ramping up. So we have every visited node here, and I think if you just iterate over this location and dump an obstacle and then just run the algorithm again and check for cycles, we are done and good to go. Yeah. I'm just gonna copy paste a whole lot of code, I think. We're just gonna do the patrol again, but instead of halting condition being... Or no, let's expand the halting condition with a cycle flag. How did we detect cycles? Instead of just keeping track of the locations, we just keep track of the guard. So yeah, let's take a look at our state here. Our state is right now just locations. Let's make it a set of guards actually. So yeah, let's rip out the original algorithm just a bit. So we just keep track of the guards. Everything else stays the same, I guess. And now we can easily detect... Yeah, now we can easily detect cycles. Let's also... let's also halt when we detect the cycle. So let's grow our state object a bit more. And let's give it a reason. Yeah. Let's give it a reason. And that's like either the guard ran away, he's out of bounds. So out of bounds, or we have a cycle. Loop, let's call it loop. For now, our algorithm right now only checks for loop. So it's like a state with reason equals out of bounds. That's how we end up here. And make it let's make it an option. So when we're running through the algorithm, we don't need a reason just yet. State is visited, dot empty, and reason is nothing. We don't need a finish reason. Finish reason, sorry. I'm jumping all over the place, sorry for that. I'm exploring this problem in my head, and my head is pretty chaotic. This is why I'm also jumping all over the place. So, plan, back in focus. We are going to alter the patrol algorithm so it detects cycles as well. And then we introduce obstacles on every node in the path, and we count the number of grids where we have like a halting or finish reason, which is found the loop. So found the loop, where do we detect a loop? That's right here, right? We have the next state, and here we add it to the set, but actually we need to do a quick check. If we already visit this exact location facing this exact direction, we have a loop. So this has to go back out. So let's do a new halting condition. If next guard is in the visited set, then we are so done. And otherwise we do what we did before, recursive call. We don't have the actual loop. We don't need the actual loop, so this will be good enough. Does it still work? Does the algorithm still work? Yeah, it stops with out of bounds, which is correct for our first iteration. And we have a set of visited nodes. And we don't need the directions, so let's do a sequence.map on the guard and just take the guard's location. And that can be a list again, so we can print it out easier. Yeah. So now for every node in the path, let's put in an obstacle and run the patrol algorithm. I would like to introduce the obstacles as an input argument because it changes. So I'm just gonna break my code to see where I reference obstacles. I only use it once, and that's in the next. So let's provide a extra input argument to this next function, and it'll break something else. And there we go. And let's just introduce it as an input argument here as well. And let's just pipe that into here. And let's just pipe it here as well. Yeah, I think we're good. So obstacles can become obstacles again. And we are piping it in as an input argument instead, using some global state somewhere. And now we can start to tweak the obstacles for every different simulation we want to run. Or at least that's the plan. So do we need to do distinct things? How many different positions could you choose? We are starting from a set. The set has no obstacles because that's the path of the guard. I think this is good enough. So we have the set of visited locations, and we create a set of different obstacles for that because we add that to single location to the obstacles, and then we just patrol a whole lot. What does patrol take? Obstacles and init. So let's just write a lambda, so we can do patrol, obstacles, and always the same initial state, right? And these are all the simulation runs we do. It's saying we have some indentation problems. I'm not seeing it. Okay, it was not an indentation problem. Okay, we have a lot of runs here. Let's just filter them. What was it? Some loop. We grab every one run where we halt because of a loop, and we just count them, right? So we have 9 simulations where we encounter a loop. And that's not correct. That's a shame. Oh, dang. 6 different positions. Why am I saying 9? What was the original path length? 41. So we're doing something, but we're doing something wrong. Dang it. Yeah, I think it's time to, or I figure out like the silly bug, or we're in for a world of debugging and printing out grids. Okay, let's take it from the top. This all stayed the same. We introduced a finish reason. And we changed the set of visited nodes to a set of guards instead of a... Ooh. Yeah, no, we don't care about visited. Okay. I have an idea. We're looping over the list of visited nodes. This one can contain duplicates, right? It's a set of guards, but sometimes a guard enters the same location, but he's just facing a different direction. So I think this is the bug. We shouldn't be doing this. I should make it a distinct list of locations instead of just a flat list of locations, because duplicates can creep in this line of code. Yeah, let's just dedupe. What's that? Distinct. Let's just distinct this. Let's see if this is the actual bug, right? before deduping... Oh god, oh god. Okay, before deduping we have 55. And after deduping... Oh, we have 41. That might actually be the bug without having to do a lot of debugging. I was this close to turning off the stream and figuring it out. And it always happens that like 2 seconds later I figure out what the actual problem is. So if this is a, what, 6? It's a 6. Okay. We got this. We're back on track. Let's do this on our input and hope our algorithm does not crash and burn. And otherwise, thanks for watching. Hope to see you tomorrow. Because I won't be fixing it today. We've been at it for an hour. That's pushing it. I have like a real job and real work to do as well. So yeah, let's keep our fingers crossed that this just works. It's chugging along, I guess. And it's taking a bit longer than I thought it would. But nothing appears to be crashing, so I'm just gonna let it run for a couple of seconds. And if this does not terminate within the next minute, we'll have to come up with a faster alternative. What could improve? We are doing lookups on a set instead of on a constant... oh, I think I just saw it finish. So yeah, the lookups is something we could improve, and probably the number of nodes we check could be decreased, but I'm not sure about that. Anyway, let's see if we got the right answer out of this. 2143 is the right answer. Definitely not the best or fastest algorithm, and we had some bugs, but we persisted today. And we are done within the hour, so I'm really happy. Let's do a quick recap and let's finish up for today. Part 1 was just calculating the path until the guard went out of bounds. I really love the twist for part 2 again. These puzzles are amazing this year. For part 2, our approach was to just take the path the guard would take and dump an obstacle in each and every one of those locations. And the second part of this part 2 thing was we needed to detect cycles, and we were almost there with our visited set, but we had to keep track of the direction the guard was facing as well, because a guard can cross the same location multiple times without actually it being a loop. Yeah, I love this puzzle. I'm having a lot of fun this year. I hope you are having fun too by solving these puzzles yourself or just watching me. If you do, please let me know below in the comments, and I would love to see you again tomorrow for more Advent of Code in F#. Bye bye.